For today's movie, you're going to need to have a ruler in addition to something to write with, and I'm going to do a little bit of color coding, so if you want to have some colored pencils available, that would be great. And you can see from this heading that write only what you need to from this slide. I don't expect you to write everything. In fact, this is a slide where you shouldn't write much at all, because the scenario we're talking about is the following. During our last lab, we used those semicircular prisms, and we always set it up so that light would enter from the air into that other material, and the other material was always something with a higher optical density, and we always got to see that light was bending towards the normal. So the plan is to just contrast that situation with what happens if light starts in the more optically dense material and moves into a material with a lower optical density. So some terms that you probably should copy down are the following. We've got HOD, high optical density, and LOD, low optical density. So once we've got those short forms down, we're going to move on to the next slide in 3, 2, 1. So your title is Total Internal Reflection, and we're going to contrast the situation between light moving into higher optically dense material or lower optically dense material. So we're going to start on the left-hand side. We're going to divide this up into 2 columns, not very long on your page. And so light moving from low optically dense materials to high optically dense materials should have the following characteristics. The light should slow down. The light should bend towards the normal. And because of that, we can simplify that statement to theta r, the angle of refraction, will always be less than theta I, the angle of incidence. So now we're going to contrast that with light moving from high optical density to low optical density materials. So we would expect the opposite. We would expect light to speed up. We would expect light to bend away from the normal this time, and that means that theta r, the angle of refraction, should be larger than theta I. So we're going to move on to the next slide in 3, 2, 1. So on this last side, what we're going to do is we're going to do some writing on the left-hand side, like that. And I'm going to do my drawings on the right-hand side. And so I'm going to draw first a line separating my 2 materials. And I'm going to label this with my high optical density below, my low optical density above. I'm going to draw in a vertical dashed line, which is my normal, and I'm going to draw in an incident ray in blue, and so I'm going to draw an incident ray like that. My theta I is there, and there will be some value for every scenario like this where theta I causes that ray to go right along the surface. So there's my theta r, and it happens to be a right angle or 90 degrees. So that happens at one very specific angle that is unique to that pair of substances for low and high optical density. So whenever that happens, that is called the critical angle. So this is a situation where I'm going to change the color to red equals theta c, the critical angle. So we have a critical angle which causes the refraction to bend to a full 90 degrees, and therefore we're going to be able to say one of 3 scenarios. First of all, when theta I is greater than the critical angle, which I'm going to draw here in purple. So as soon as I go above, so there's, I'm going to put that in purple, so I'm going to mark that over here. When theta I is greater than the critical angle, we're going to see total internal reflection. So the ray is going to come out here. And you noticed a little bit of that when you were doing your lab before. However, in the scenario where theta I is less than theta C, and I'm going to draw that in the yellow, that means that we've got a ray here, and therefore we're going to get some angle of refraction out there that's less than 90. So I know that diagram is starting to look a little messy, but what we're trying to say is that when theta I is greater than the critical angle, you are going to get no refraction going out the top in the low optical density. You're just going to get reflection, which is that total internal reflection, which is your title. However, when you get theta I is below the critical angle, you get refraction, but you're also going to get a little bit of reflection. So I'm going to put that in a faint dashed line. It's not really a ray extension. What it is just that there's going to be less of it. Lastly, the larger the value of the critical angle, so the further over that is, the lower the material's optical density, because if it's got a high optical density, it doesn't take a lot of angle to get that huge bend. Lower optical density means you've got less bending, so you got to get the critical angle bigger to make that work. So I know the diagram's a little messy. When we're in class tomorrow, we're going to make it a little bit neater by putting this on the foldable where we can separate those scenarios. Thanks for watching.